Have you ever tried to catch something you literally can't see? Something moving faster than a jet plane and so tiny that it makes a single marble look like, well, like planet Earth? It sounds impossible, right? But that's exactly what we're talking about today. We're going to dive into the absolutely incredible feat of trapping a single atom.
So here's the game plan. First, we're going to talk about why on earth we'd want to do this. Then we'll get into the monumental challenges involved. After that, we'll open up the amazing toolkit that scientists use, figure out how they actually confirm their catch, and then finally, we'll take a peek into the quantum future that this whole thing is building.
All right, let's kick things off with the biggest question. Why? Why go through all this insane trouble for one atom? Well, because controlling a single atom isn't just a neat science experiment. It's the key that unlocks a whole new era of technology.
And this quote just nails it. You see, for the last century, we've been building things out of atoms. Big clumps of them. But now, we are right on the verge of building things with them, one by one. This isn't just another small step. This is the literal foundation for a tech revolution on a scale we've never seen before. And the applications? They are just staggering. We can use these little trapped atoms as qubits. That's the heart of quantum computers, which could design new medicines in days instead of decades. They can become atomic clocks so unbelievably precise they would lose just 1 second over the entire age of the universe. And get this, they even let us build perfect little models of reality to discover new materials we haven't even dreamed up yet.
Okay, so the payoff is obviously huge. But the problem? Well, it's a pretty massive one. We are talking about isolating and controlling one of the most fundamental, slippery building blocks of our entire universe.
Just let that sink in for a second. Seriously, imagine you are standing on the moon, and your job is to find and pick up one specific single marble somewhere on the surface of the Earth. That is the mind-bending, ridiculous scale we are dealing with here. It's a challenge that just seems completely impossible.
And it gets worse. You have to build a vacuum chamber that's emptier than deep space, just so your atom doesn't accidentally bump into anything. Then, you have to figure out how to stop it, because at room temperature, it's zipping around at hundreds of miles an hour. Oh, and on top of all that, you have to deal with quantum mechanics, where the atom is so fragile it basically exists in a fuzzy cloud of possibilities, and even the tiniest little disturbance can completely ruin everything. So, how in the world is this even possible?
Well, the answer lies in a very, very clever toolkit. Scientists have developed some absolutely brilliant methods to get around these hurdles, and it all starts with tackling that first big problem, the insane speed of the atom.
It sounds like pure science fiction, but it turns out that light itself can actually push things. By hitting an atom with photons from a laser at just the right frequency, you can slam the brakes on it. Imagine trying to run full speed through a blizzard, where every single snowflake is hitting you head-on. You'd slow to a crawl, right? That's basically laser cooling. It brings an atom's temperature down to a fraction of a degree above absolute zero.
Okay, so once the atoms are super cold and slow, you've got to hold them in place. And there are 3 main ways to do this, and each one has its own special trick. You've got the magneto-optical trap, the optical tweezer, and the ion trap. Let's break down how they work.
So the first step is often something called a magneto-optical trap, or a MOT. This thing is amazing. It uses 6 laser beams, all pointed at the center, to create what scientists wonderfully call optical molasses. It's like a thick, gooey trap made of light that slows the atoms way down. Then, a magnetic field creates a kind of sticky spot right in the middle that the atoms get funneled into, forming this small, cold cloud of atoms.
Now, if you want to grab just one neutral atom out of that cloud, you can use optical tweezers. This is, for all intents and purposes, a real-life sci-fi tractor beam. You take a single, powerful laser and focus it down to an incredibly tiny point. That intense spot of light actually attracts a single atom and holds it right there. It's perfect for building big arrays of individual atoms, almost like you're using an atomic-sized construction set. The other major technique is the ion trap. For this one, you take an atom and you knock an electron off, which gives it a positive charge. Then you create this really clever saddle-shaped electric field. Now the charged atom, the ion, wants to roll off the saddle, right? But by rapidly flipping the field back and forth, you trap it right in the middle. It's kind of like trying to balance a marble on a Pringles chip by shaking it really, really fast. And these traps are incredibly stable. They can hold on to an atom for days. Okay, so you've set up your lasers, your magnets, your whirring electric fields. You think you've caught one, but how do you actually know? I mean, how do you see something that is, for all practical purposes, completely and utterly invisible?
Well, the answer is you make it glow. You shine another specific laser right onto the trapped atom. The atom absorbs that light, gets excited, and then spits it back out as photons, particles of light, in all directions. It is exactly like flipping the switch on a tiny, one-atom-sized light bulb. And a super-sensitive camera is sitting there, waiting to catch that faint little glimmer of light.
And this is the moment of truth. If that camera detects even a single photon coming from that exact spot in the trap, you've done it. That tiny little blip on a screen is your definitive proof you have successfully trapped and taken a picture of a single atom.
So trapping one atom is this monumental Nobel Prize-winning achievement. But the real goal, the ultimate dream, has always been to go from just one to many, to actually build complex machines, atom by atom.
And the challenges now are really all about two things: protection and scale. How do you protect these incredibly fragile quantum states from the slightest little vibration or magnetic field from the outside world? That problem is called decoherence, and it's a huge hurdle. And then how do you scale this up? How do you go from trapping one or two atoms to controlling hundreds or even thousands, all working together perfectly? Solving these engineering puzzles, that's the next great quantum leap.
So think about it like this. For the very first time in human history, we've learned the fundamental alphabet of the universe. We can pick up the letters A, B, C. Right now, we're just learning how to spell simple words, but soon we're going to be writing sentences, and then chapters, and then entire sagas. So the real question is, what incredible new stories about reality, about medicine, about computation are we going to be able to write?